So, in this topic of belt friction, or suppose we have a cord wrapped around a post. So, we have this and there is a fixed pillar or a post. We will derive this formula for a circular post or circular pulley, whatever you may call it, but in general this could work even for non-circular things. So, here what happens is that when we say that the post is frictionless or there is no friction on the belt, then we get T1 is equal to T2. But if there is friction, then it turns out that for impending motion just to take place, T1 will not be equal to T2 and this will be related to the friction force. Now, in this and the next class of problems which we will do, what we do is that we apply this relation friction is equal to mu n, but so far we have applied it at either a point or in an integrated way, that for the entire contact we take it as a single normal reaction. But this relation that friction is equal to mu n for impending cases is also valid even if we have infinitesimal forces or forces. So, now if we talk of force per unit area, then the normal reaction would be equivalent to pressure. A force per unit area in the normal direction is what we call as pressure, and we will have a frictional force per unit area or per unit length along the tangential direction. And once again the frictional force per unit area is related to the normal reaction per unit area by the same relation that friction will be equal to mu times n when we have slip or impending slip, otherwise it will be less. So, the same relation is to be used, but it may we will use it per unit area or per unit length. Now, of course, there is a cord wrapped around a post. You have seen many problems, and this is probably you see a small child holding a truck on the other side, that there is a truck which is wrapped around a post and the child is holding the truck. Now, the child need not be a superpower, he need not be Hanuman to hold the truck. All he has to do is just wrap it around the post 2-3 times, and then even with a small force he will be able to hold the truck. And that is, at least some of you, if you are familiar, the relation between these two tension goes like exponential of the coefficient of friction times the angle of wrap. So, here what we do is we look at the 2 points from where contact is taking place, or where you are just from the start of the contact to end of the contact, and look at this included angle, and this is the angle which will be related, and that is what I was saying. If you wrap it 2 or 3 times, then this angle beta keeps on, for each wrap, full wrap, the angle beta becomes 360 degrees or 2 pi. So, let us now try to derive this relation between T1 and T2. So, we have a belt which is on a post, and the 2 ends to the belt, it starts contact at this point and leaves contact at the other point. And in this case we are looking at the case when the belt is about to slide to the right. That means you are pulling the belt from the right. You will realize that, and that is the only sort of confusing thing which comes in these problems, is which side tension is greater. So, here what you are doing is the belt is being pulled, the impending motion on the belt is to the right. Okay. So, what we do here is we have to relate T1 and T2 when the belt is just about to slide to the right. So, what we do is we draw a free body diagram. We have this belt, we draw a free body diagram of a portion of the belt. So we look at a portion of the belt, we are starting from this end because the belt will slide to the right. So at an angle theta, we choose a sector of angle delta theta, and we draw the free body diagram of the belt between the points P and P prime. P starts at theta and P prime is located at an angle of theta plus delta theta from P1. So we draw free body diagram of the belt. Now this angle, the total subtended angle is delta theta. Let the tension on the left side, which will be at an angle of delta theta by 2 from the horizontal, let this be T. On the right side, let the tension be T plus delta T. Okay. So we want, eventually when we integrate this, we will get the difference between T2 and T1. At the leftmost point T is T1, at the rightmost point T plus delta T will be T2, isn't it? So because we are looking at one portion of the belt, this angle is delta theta, this angle is T, that is at T plus delta T. So now the normal reaction which acts from the drum on the belt, we write it as delta N. This is the normal force which is acting on the belt. Now because the belt is about to slide to the right, it will have a friction force which will be acting, which will be towards the left, and we call that as delta F. So basically all the deltas represent that these are forces on infinitesimal areas, and because this is just about to start sliding, this will become equal to mu s times delta N. If it is a case of no slip, then it will just become equal to less than delta F will be less than mu s delta N, but when it is just about to slide, when the belt you are just about to pull, at that point it will be equal to mu s delta N. So given these are the different forces acting. So then it's a simple this thing, we work out, take sum of all the forces in the x direction is equal to 0. So on the right we have T plus delta T, which is acting at an angle of delta theta by 2. So we get T plus delta T cosine of delta theta by 2. On the left side we have T cos delta theta by 2, and then we also have the friction force minus mu s delta N. This is equal to 0. So this is sigma fx. We do sigma fy is equal to 0. So there is a delta N, and then we have minus T plus delta T sin delta theta by 2 minus T sin delta theta by 2 is equal to 0. So now from here first we will do is find the value of delta N. So delta N will become equal to will be equal to 2T sin delta theta by 2. Then there is a second term plus delta T sin delta theta by 2. Now this term is what we will neglect because there are two differential elements, delta theta and sin of delta theta actually becomes delta theta by 2. So therefore we will neglect this and delta T. So that second order term is neglected. So we get the value of delta N, and that delta N is feeded in the first equation. So when we do that, what we get is delta T cosine delta theta by 2 is equal to mu s into this thing times delta theta. So this must be equal to 0. I think I have not put this. So in the limit you take delta theta going to 0, we have sin delta theta by delta theta, so that will become equal to 1, and when we do that, that means angle theta is in radians, not in degrees, and so what we get is eventually dt by d theta minus mu s t is equal to 0. That is the relation which we will get for this thing. Now we separate the variables and integrate, which is a standard this thing. So dt by t is equal to mu s d theta. So from here, and then you integrate, t goes from t1 to t2, theta goes from 0 to beta. So when we do this, we get log of t2 upon t1 is equal to mu s beta, and that gives us a relation between the two belts, that T2 upon T1 is equal to exponential mu s beta. So that means with the angle of wrap, the tension increases along with this in terms of this in a exponential way. This is something which we know, even we use this many times without probably realizing this. When you tie a knot, actually you are using a principle like this, because in the knot when you tie, the rope itself is being used as tied on the rope itself. So there is a, so the force required for the knot to move on one side will be related to the other by an exponential factor of the angle of wrap. Of course, in the knot we never don't realize this, because the post as well as the belt are the same things, but that is what you actually do when you tie a knot, and one side when you pull, then only the knot opens, other side you pull, it will not open. So therefore that's how this principle of angle of wrap there works on the knot also. So this is used over many these things. Now the same concept, I'll just, we use this also we have often seen situation when you have what we call as a belt drive, that we have, I don't know how many of you have seen what's called an aate ki chakki. Has anyone seen the place where the wheat gets? So there definitely you must have come across this two wheels, and let me draw. So I think you have a small wheel, of course, yeah, there is a simpler example of the cycle and the chain. So you have a belt which is connecting the two wheels. So this is what we have, belt connecting two pulleys. Typically in this, and as in the case of a cycle, in fact probably cycle is a more common example. So what you have is one of these two wheels is the one where you are applying power. In a bicycle it happens to be the rear wheel, where in fact it is the sprocket on which through the pedal you are applying, not the rear wheel gets the power, that's but then you are applying it to the sprocket. So there is a driver wheel which I will say, and this is the direction in which you will do it on a bicycle. Okay. So we have a driver wheel like this, and we have a second wheel which is a driven wheel. So this, of course, your problem will specify which is the driver wheel, which is the driven wheel. This is something which you will design. You will provide power to one end and you will extract power from the other end. So we have a driver wheel and a driven wheel, and the driver wheel will rotate in a particular way. Now the driver wheel is rotating, the belt or the chain which is in touch with the driver wheel is moving because it is in contact with the driver wheel. So here the belt is moving because of the driver wheel. Which will move faster, the driver wheel or the belt? When it is no slip, both will move at the same rate. But what is causing it is the wheel or the pulley which is causing the belt to move. Okay, and in this case what happens is the belt moves, and because of the movement of the belt the wheel moves. So that is how this transmission is taking place. In one case this is being moved by an external source, this starts to move, so the belt starts to move, and because of the motion of the belt this starts to move. So therefore fundamentally there are two different things. In one case the wheel starts to move, which is what causes the belt to move, and the belt by its chance it causes the other wheel to move because of its motion. Okay. So this is the case. Now what we have is, if suppose I am, so basically what I am doing is I am showing TA and TB, I should not show it like this without a cut, because if I am cutting it on the right side, then the two tensions in the two sides will be TA and TB. Now there is often a confusion, which of them is bigger? Is TA bigger or TB bigger? So now, no, so see TA and TB will be the same on both the wheels. On both the belts, if I look at the right side, I will have a TA here and a TB there. Now, how do we figure out which is bigger, TA or TB? How do we get that? We can get this from two facts. One from the fact that this is a driver wheel, that means this wheel will move, and that is what is causing the belt to move. If the belt is moving, then in which direction will the friction move? The belt is moving like this, the wheel is moving faster. So that is one way of getting it. The other way of getting this could be, and which I find straightforward, is that because this is a driver wheel, that means a moment is being applied on this wheel in this direction. So if I am applying a moment in this direction and I do a moment balance, what I will get is TB plus this moment must be equal to TA. If I do the moments about the center, then TB times R plus the moment which is being provided, because this is the driver wheel, it provides the moment. So a moment is being applied on this. So TB plus M is equal to TA. So that means TA will be bigger. So this is what is called the tight side, the other side is called the slack side. We are not going into theory of belts, but this is just to determine which is bigger. So on the driver wheel, so if I draw free body diagram of the driver wheel, TA, TB, so then I have TA times R is equal to okay, and you will get the same direction, same thing from the friction argument also. The wheel is moving faster than the belt, or just at that time wheel will have a tendency to move faster. So that means the wheel is moving in the forward direction, so belt is moving in that direction. So if the belt is moving in that direction, friction on the belt will be in the clockwise direction. So therefore again friction plus TB must give us TA. So both from friction argument as well as the moment argument, but the moment argument please put it on the driver wheel and the direction of motion. So then there will be no confusion. Now so that means we have a case, and similarly when you do the analysis on the other side, we will get the same thing. But now the question comes, if it's a case of limiting motion, just about to slide, on which end will the belt slide first? See, we have an angle beta on the left side and or beta 1 on the left side, beta 2 on the right side. On which of these will we use TA upon TB is equal to e to the power of mu beta? Beta 1 or beta 2? Both the sides, the tension in the belt will be the same, assuming it is non-accelerating. So on the right side and the left side, the tensions are the same. So now this is beta 1, this is beta 2. So the question I am posing is TA upon TB is equal to e to the power of mu beta 1 or e to the power of mu beta 2. How do we find this? Or which of these is correct. Where will the slipping take place first? At a lesser angle or a bigger angle? At the lesser angle. See, Ta upon Tb has to be one of these, and so for just impending slip, it has to be the lower of the two values. If it has to be lower of the two values, that means you have to look at beta 1 and beta 2 and see whichever is lower. Whichever is lower, slipping will take place at that point. In this case, it happens that beta 1 is less than beta 2. So that means this relation will be valid for beta 1, because if we apply it for beta 2, then it will already slip for beta 1, and that will not be allowed. So therefore, we look at the lower of the two angles. That is where the limiting condition will be reached first. So that is how we work this out. Okay, so how to find this? So slip. So this will at the end where the angle is less. So look for lesser of the two angles. Look for the lesser of the two angles. An example of this in the book: a flat belt connects a pulley A to pulley B. A similar thing. Now here the coefficients of friction are given between both pulleys and the belt. The smaller pulley has a radius 1 inch, the bigger pulley has a radius of 8 inches, and this is the driver pulley. So this is the motor which is running, and the direction is clockwise. So it is basically the red arrow shows the direction of the driver wheel. The driven wheel will of course move in the direction like this. So it will move in the, so this one is moving like this, that will also move in the same direction. That's how it will. Now firstly, here the angle of contact on the smaller pulley will be less. On the bigger pulley it is more than 180. On the pulley B, the angle of contact is less than 180. So therefore the basically we have to apply T1 upon T2 on this pulley. And once again, which of the tensions is bigger? So we draw the free body diagrams of the two pulleys. So first I draw the free body diagram of the smaller pulley. On the smaller pulley, I have this angle of wrap is 120 degrees. This is T1, T2, and as before, as we said, this tension is bigger. It's the same situation as what I discussed. It's the same direction of motion, so therefore this tension is bigger. This is T1. Now this was given in the problem. Let me see where this this one says 600 pounds. Okay, a felt belt. I think somewhere something is missing. This data that this should be 600 pounds is already a part of the problem. Have I think the full problem has not been, this has to, no, this has to be moved down. I think we have hidden a part of the problem. It says the tension in the top part of the belt is 600 pounds, and we have to find the moment, how much is being extracted from the driven pulley. That is what the problem is. So therefore, given that this is 600 pounds, first we draw the free body diagram of this belt and we work out the value of T1. Once I work out the value of T1, which comes, and as I said, to get this we look at the lesser angle, and once we have this, then we draw the free body diagram of the other pulley. On the other pulley there will be some contact forces, it is there, then the pulley is rotating in this way. So therefore the whatever moment you are extracting, that will be in the same way. So on the pulley, this will put a moment in this direction, because this is the driven wheel, you are extracting the moment from it. So what it applies on this will be in the other direction. So therefore we have this MA which we wanted to find out. We know the two tensions. So therefore the difference of the tensions multiplied by the radius of the pulley will give us how much moment will be, or the torque which can be extracted from the pulley. So this is how we work out the problems. Okay. Now there is, I think these are all straightforward problems. The last type of problems which we have in friction, and which I'll at least maybe just we have not done, there are no problems of this in the homework etc. So I'll just maybe briefly show this. I think the book has some. Suppose we have two surfaces in contact. This is what I call a clutch type of a problem. This is what happens in a clutch of a vehicle, that both the sides there are rotating. Here I have shown one side as fixed. And there see, there is a contact, there are two surfaces which are rotating. One of them is again a driver surface, the other surface is in touch, and it is because of friction that the other wheel also rotates, and we transmit motion of rotation through friction. So basically somehow when we talk of friction we always think of it as negative, but it is always, it need not always be a negative thing. So here what we have is that, let us think that, sorry, this is a torque, this body which is there is rotating, and at the same time we apply a force to hold this on the wall. So to maintain the contact we apply a normal force, and at the same time this body is rotating. So here in these type of problems what we want to find out is what is the frictional moment which comes. At the surface there is a friction force, how much is the moment which will come because of friction. And in these type of problems again what you have to do is look at an area of contact, or infinitesimal area, and there you work what is the friction force on that area. So that will be related to basically coefficient of friction times the pressure, force per unit area. Integrate it over the entire surface, and it will not be a force, it will be a moment, because friction force as this rotates, see, you will see this, as this rotates, then the friction force will cancel out. Friction in this case does not provide a force, it provides a couple, because if you add up all the friction forces they will cancel, but they are acting in such a way that it forms a torque, and that couple you can find out by relating the friction force to pressure. So these type of problems I am not doing, but this is another class of problems which comes in the frictional this thing. The coefficient of friction, let us some one or two general things and then I will just end this discussion on friction. Coefficient of friction, does it have to be less than 1 or can it be bigger than 1? It can be anything. Really, like there is another coefficient we will do, coefficient of restitution, that lies between 0 and 1, but friction coefficient can be anything. The other thing, when we walk, in which direction does the friction force act on our leg? Forward. Actually, because what is happening is when we walk, the knee roll, we are rolling the leg about the knee joint, and we hit the ground in the backward direction. So on the foot the friction force comes in the forward direction, and actually it's the, if we look at the body overall, the external force which helps us to walk is the force of friction, which is in the forward direction. But again it is the same thing, that relative to this knee, when you try to just slip yourself forward, you will not be able to. For you to walk, the leg has to hit the ground in the backward direction, and that is what provides the forward force on the body so that the body moves. Similarly, when we look at a car, just starts to move, when the car is in the accelerating phase, in which direction does the friction force act? Forward direction. It is friction which provides the acceleration. in the driven wheel, whichever is the wheel which is being driven. See, what happens in a vehicle is, if you if this is the vehicle, if one of the wheels is a driven wheel, the other is not a driven wheel. So, suppose the rear wheel is the driven wheel, the front wheel is not a driven wheel. Now, for this to move forward, it has to be, sorry, if this is moving in this direction, then let me first erase this, because this will create confusion. So, if this is to move forward, then this has to be the angular velocity. Okay. Now, here what will happen is that means a torque has to be provided by the axle on this wheel in this direction. So, this torque has to be provided for the vehicle to start moving forward. On the front wheel, there will be no torque. It comes only on the driven wheel. Okay. Now, let us take a case of a vehicle which is moving on up an incline. Now, what you will realize is, in fact, we solve problems, we show friction force only on the driven wheel. We do not show friction force on the free wheel. Why is that so? Let us take a case of a truck moving up an incline, and like this, and we draw a free body diagram, we show a normal force and we show a friction force, and this one we show only normal force, we show the friction force as 0. Why is that so? So, this is the driven wheel, this is the free wheel, and actually this comes from the fact that if you draw the free body diagram of the driven wheel, what all comes here? There will be forces from the axle, and there will be a couple. On this wheel, what will happen? You will just have forces which are coming from the axle, we have the weight, there is no couple. So, now even if you show a friction force, when you do moment balance, you will get friction is equal to 0. Whereas in this case, friction has to be there to be able to provide, to take care of the torque. If in this case you show a friction and you do a moment about center is equal to 0, you will get friction is equal to 0. No, if it is moving with a constant velocity, if it is accelerating, then it will not. But in this case, if there is a torque being provided, then friction will have be there to take care of that torque. Another way of looking at this, you can think of this wheel as a 2-force member. Why is it a 2-force member? Only forces are acting at 2 points. So, that means the net resultant has to pass through this. So, there cannot be any force in the tangential direction here. So, friction here has to be 0. Whereas in this case, this is not a 2-force member. There is a torque acting on it. So, therefore, friction has to be there to take care of this force. Okay.